In the last section, we talked a little bit about differentials towards the end. In this section, we're going to really do a lot more with it. And just to know that the differentials would be like dy equals f prime of x dx. And it gives you an estimate of what that change would be. So instead of actually having to calculate f of x plus a minus f of x, it gives you the estimate. So differentials provide us with a way of estimating the amount of function changes as a result of small change in the input values. So that's our differential formula. For this first example, it says for each of the following functions, find dy and evaluate when x equals 3 and dx equals 0.1. So for our first one, we have that y equals x squared plus 2x, so that y prime would be 2x plus 2. So dy, that small change, would be f prime of 3 times that small change, the dx is 0.1. So that's going to be 2 times 3 plus 2 times 0.1, which is 0.8. And for the second one, y is cosine of x. So y prime would be sine of x. And by the way, I'm using f prime and y prime interchangeably. So our dy would be, sorry, that's negative sine of x, would be negative sine of 3 times 0.1. And I run this through my handy dandy calculator, and I get, well, I just left it like this because this is how the book left it, negative 0.1 sine of 3. That's it. Okay, move on. For y equals e to the x squared, find dy. So our y prime is going to be e to the x squared times the derivative of x squared, which is 2x. So the dy would be 2x e to the x squared dx, where dx will represent that small amount of change in the input value. And that's it. Okay, let's go on. So this would be the way to calculate the actual change, is that delta y equals f of a plus dx minus f of a. And of course, we saw in the previous part of this section the linear approximation format. So if dx is small, f of a plus dx is approximately the linear approximation. So you could look at it that way. So notice that these will go away. So it's f prime of a dx. Okay, let's go ahead and talk about this again. We're looking at a curve with a tangent line, and we see that even in this area, they're pretty close together. So it's close enough to use this model to some degree, but there is a point where you say that it's too far apart. Okay. So for the next one, we're going to calculate both the delta y and the dy. So our y equals x squared plus 2x. We saw this earlier. And the delta y for this is going to be f of, that's 3 plus the 0.01, so 3.01 minus f of 3. So that's going to be 3.01 squared plus 2 times 3.01, and then minus 3 squared plus 2 times 3. And for the delta y, we come up with 0.81. And for our dy, we're looking at f prime at 3 times the 0.1. And what is our y prime? That's 2x plus 2. So 2 times 3 plus 2 times 0.1, and we get 0.8. So we see it was a lot less work to do the dy, and we got 0.8, and that's pretty close to this 0.81. Okay, moving on. Try another one like this. So it's the same setup, but this time our dx is 0.2 instead of 0.1. So again, our y prime is 2x plus 2. So for our delta y, we're looking at f of 3.02 minus f of 3. So that's going to be 3.02 squared plus 2 times 3.02 minus 3 squared plus 2 times 3. So in this case, it comes out to be 1.64. And the dy would be that same f prime at 3 times now 0.2 instead. And we've seen that f prime of 3 was 8. So 8 times 0.2 gives us 1.6. So we see that's still pretty close, but it's a little further apart, because last time we saw it, it was a 0.8 and a 0.81. This time it's a 1.6 and 1.64. So the distance between these is growing a little bit. And this is due to the dx that being further, it's a bigger step than we saw before. So that's a bigger distance from the reality. Okay, so in doing that, we would talk about the error that we're really seeing, the error on what these values, these estimations are producing. So it's important to be careful of what they call propagated error, which means you have a value that's off, and you keep using that value, and you end up with a number that's far from what the reality is. And we often see that if we round off too much in our calculators when we're doing problems, we get propagated error. And so when you're trying to plug things in for an assignment, it's not always going to be there. So we know that the delta y is approximately dy, but we can also calculate how far off we are. Suppose the side length of a cube is measured to be 5 centimeters with an accuracy of 0.1 centimeters. So if that's our measurement, we have our volume equals x cubed, because that's our side. So our dx has a range of values. So it says use differentials to estimate the error in the computed volume of the cube. So our dv is going to be 3x squared, the derivative of x cubed dx. So we need to come up with these values. And we'll compute the volume of the cube if the side length is 4.9 and 5.1. Compare the estimated error with our actual potential error. Okay, so the dx, this change of this small variation in value, is going to vary between negative 0.1 and 0.1. So that means our dV, I think what happened to that, it was 3x squared times dx. So to get to this dV, that's 3x squared dx. I can multiply everything by 3x squared dx. So 3x squared 3x squared times the negative 0.1 is less than 3x squared dx less than 0.1 times 3x squared. I'm onto something here, so this is just random. That this middle term becomes our dV, and we can come up with the boundaries of that. So our dV would be negative 3 times, and the x was 5, times negative 0.1. I shouldn't say it. The negative's over there now, so I could just not need it here. Times 0.1. And then it would be the 0.1 times 3 times 5 here, 5 squared. So it's negative 7.5 is less than dV less than 7.5. So that's that variation that could occur. So for the second part, it is asking us to compute the volume of the cube if the side length is 4.9 and 5.1 and compare it to the estimated error with the actual potential error. So for B, our volume at 4.9 is going to be 4.9 cubed, which is 117.649. And the volume at 5.1 is going to be 5.1 cubed, which is 132.651. And the volume at 5 is just 5 cubed, which is 125. So in looking at delta V, we have two calculations. The low end was that 4.9, so it would be 117.649 minus the 125 is less than delta V, less than, I should say less than or equal to, the bigger value, which is the 132.651 minus 125. So this gives us the range of negative 7.351 is less than or equal to delta V less than 7.651. And what I want to stress here is that our dV from just above there was between 7.5 and negative 7.5. So very similar numbers there. Pretty interesting. Okay. Estimate the error in the computed volume of a cube if the side length is measured to be 6 centimeters with an accuracy of 0.2 centimeters. So again, our dV is going to be f prime of x dx. So dV is going to be, and so I guess I should say f of x is x cubed. F prime of x is 3x squared. So it's going to be 3 times 6 squared times 0.2. And that's going to be 21.6 centimeters cubed. Okay. Okay, moving on here a little bit. We've got a couple more problems to look at. So we can talk about relative error. And that's going to be our delta Q over Q. And we can talk about our percentage error as well. It's a relative error expressed as a percentage. So let's look at a situation with this. An astronaut using a camera measures the radius of the Earth as 4,000 miles with an error of plus or minus 80 miles. Let's use differentials to estimate the relative and percent error of using the radius measurement to calculate the volume of the Earth, assuming the planet is a perfect sphere, which it's not. So the radius is 4,000 miles. And the error is plus or minus 80. So our volume for a sphere is 4/3 pi r cubed. And so the dV would be 4/3 pi times 3 r squared. And the 3's cancel. And we're left with our dV being 4 pi r squared. Oh, and I forgot my dr. Okay, so our dV then will have a range of values. So it's negative 4 pi times the radius, which was 4,000 squared, times the dr on the negative side. So it's 80 on the other side, but the negative here is out front. So times 80 less than dV less than 4 pi times 4,000 squared times 80. And what we're looking for is dV over V. So our V is going to be 4/3 pi times 4,000 cubed. So what we have is negative 4 pi times 4,000 squared times 80 over 4/3 pi times 4,000 cubed is less than dV over V. It should be less than or equal to dV over V less than or equal to negative 4 pi times 4,000 squared times 80 all over 4/3 pi times 4,000 cubed. Okay, so what this is coming out to be, it's negative 0.06 is less than dV over V, less than or equal to dV over V, less than or equal to 0.06. So it's a 6% error. Okay. And then we have one more to look at here. Very similar. Determine the percent error if the radius of the Earth is measured to be 3950 with an error of plus or minus 100. So very similar final calculation. So it's negative 4 pi times 3950 squared times 1,000 over 4/3 pi times 3950 cubed is less than or equal to dV over V less than or equal to 4 pi times 3950 squared times 1,000. No, it's 100, not 1,000. Over 4/3 times pi times 3950 cubed. Cubed. And so that comes out to be 0.076 is less than or equal to dV over V. Less than or equal to 0.076. So it's 7.6% error. So as our dV went up and actually the radius went down, the error went up, obviously. Okay, hope that helps. See you guys soon.